A rectangular tank with an open top can hold up to 32 feet cubed of liquid. What are the dimensions of the tank that require the least amount of material to build? So I'm going to start by drawing myself a little picture here. Or trying to draw a little picture. So we have a rectangular tank with an open top. So we'll say here is our part of our rectangular tank with an open top. Good enough. All right. So we have a length, a width, and a height. And it's open on our top here. Now we also want to note that this rectangular tank can hold up to 32 feet cubed of liquid. So we are given a constraint here. We have our constraint equation is the volume equation. We have that our volume here can be no more than 32 feet cubed. And since we have the volume of a box, we can further simplify and say that this is the length times the width times the height equals 32. And then don't forget your units. 32 feet cubed. All right, so what do we want to find? We want to find the dimensions of this tank. So we want what is x, what's the length, what's the width, what's the height, such that the surface area is minimized. So if we have and we know it's the surface area because it's the least amount of material to build. So we want the dimensions. So what are the dimensions such that the surface area of this rectangular tank is minimized? So we can think about our surface area here as the objective equations, what we want. So our objective is the surface area. And again, so the surface area is the sum of all the faces of our box or our rectangular tank. So taking a peek at our picture here, we can start with our base. We have one surface for the base. So we can say that our surface area S is equal to the area of the base, which is X times Y, plus we have the area of the surface in the front, which is also in the back. And so what are we multiplying together here? We're multiplying together the length and our height. So we can say that that's plus 2 times xz. And then last but not least, we also have the area of the faces on the side here. So we have one on the left-hand side as well as one on the right-hand side. So that's going to be plus 2. Again, we're multiplying the width times the height. And so this is the objective equation. This is what we want to minimize. But we have too many variables here. So what we want to do is rewrite the surface area in terms of just two variables. So that we can use our second partial derivative test. So what we're going to need to do is use our objective equation to solve for one variable, and then we'll be able to plug that equivalent equation into our surface area. All right, so let's give ourselves more room. Okay, so again, the first thing we want to do here is rewrite the constraint equation. And so let's see, I'm going to solve, you can solve for any of the variables, they'll all work. I'm going to solve for z. Oftentimes here, as you're solving, if you're finding that your numbers are getting big fast, try solving for a different variable. So we'll see how this one goes. So we have our constraint equation here, x, y, z equals 32, and we're solving for z. So we have z is equal to 32 divided by xy. So we'll now take this and we're going to substitute it into surface area. Or we can even say substitute it into the objective equation. Right, so notice here, if we're looking at our objective equation, we have two z's that we're now going to replace with the z of our constraint. So our surface area S can now be rewritten as x times y plus 2x multiplied by 32 divided by xy plus 2y multiplied by 32 by xy. And we can simplify. We see these x's will cancel each other out, the y's will cancel each other out, and we are left with our surface area is now defined as x times y plus 64 all over y plus 64 all over x. And we know that we're going to need to solve to find our first order partial derivatives. So might as well go ahead and we'll rewrite this. So I have x times y plus 64 multiplied by y to the negative 1 plus 64 multiplied by x to the negative 1. And so we have now successfully rewritten the surface area in terms of just x and y. And we're ready to find those potential critical points. So to get those critical points, we need the partial derivatives. So I have the partial derivative of the surface area with respect to x is equal to y minus 64 times x to the negative 2, or y minus 64 by x squared. And the partial derivative of the surface area with respect to y leaves us with x minus 64 times y to the negative 2. And we can simplify this to x minus 64 divided by y squared. So we have a system of equations here that we want to solve. And our system of equations is defined by the partial derivatives with respect to x and y set equal to 0. So I have y minus 64 divided by x squared is equal to 0 as equation 1. And equation 2 is x minus 64 divided by y squared is equal to 0. So we're now ready to go ahead, pick your favorite equation here, your favorite partial derivative, and start solving for one of the variables. So I'm going to start by solving the partial derivative of this surface with respect to x set equal to 0. So we have y minus 64 divided by x squared set equal to 0. And we can say that that is equivalent to y is equal to 64 divided by x squared. Perfect. So we can now go ahead and we'll substitute this into the other partial derivative, or into the other equation, the partial derivative of our surface with respect to y. So notice we have a y in the denominator of that equation. That's our second equation. So we are substituting or replacing that y with what we just found. So I have x minus 64 all divided by 64 all over x squared squared. And that is set equal to 0. And now we need to simplify. All right, have no fear. We're not going to actually square 64. We can simplify this. So we're going to have x minus 64 all divided by, I'm just going to rewrite this as 64 squared all over x squared squared, which is x to the 4th. Right, I distribute by squared. Don't forget that's all set equal to 0. And we say, hey, there's a fraction in our denominator. So we know fractions in the denominator flip. I have x squared minus 64 multiplied by the reciprocal of the denominator, which is x to the 4th, all over 64 squared. And look at that, we can simplify. So 64 cancels with one of the 64s in our denominator. And we're left with the simplified expression x minus x to the 4th all over 64 is set equal to 0. And I don't want to work with fractions anymore, so let's get rid of it. I want to multiply both sides of the expression by 64 to remove the fraction. And we are left now with 64x minus x to the 4th is equal to 0. And remember, factor for your safety. So we can factor that common x out in front. So I have x multiplied by 64 minus x cubed is equal to 0. And we have our two cases. X is 0, which is nonsense in this situation. And then we have 64 minus x cubed is equal to 0, which simplifies to x is 4. And so I mentioned that this is nonsense. Only in this case. Normally this would be fine. But remember, x is a dimension. Right? So you can't have a 0 dimension. That's nonsense. So we can automatically, you could of course double check this with your second partial derivative test to confirm that this x equals 4 is the critical point. But again, we're using our logic here. X equals 4 is going to be our critical point. And we can use this to find y and z. So we'll use x is equal to 4 feet to find the missing dimensions. The length, or excuse me, the width and the height. See, we had that y was equal to 64 all over x squared. So you can say that y is equal to 64 all over 4 squared, which is 16. And we know that 16 goes into 64 4 times. So our width here, the y dimension, is also 4 feet. And now we'll use both x and y to find z. So remember that z came from our constraint, which was 32 divided by xy. So we have z is equal to 32 divided by 4 times 4, which is 16. And we know that 16 goes into 32 2 times. And so our height is 2 feet. So my sketch at the beginning was not to scale, but it helped us arrive at the right conclusion. So we have our length, we've got our width, and we've got our height. such that the volume of this tank is going to be 32, and that we've minimized our surface area. So you can say, therefore, the dimensions requiring the least amount of material to build or that yield a minimal surface area are 4 feet by 4 feet by 2 feet.